Finding the distance between a point and a line in two-dimensional space. Consider the line ax plus by plus c equals 0. We want to start by showing that a vector normal to the line is given by a comma b. Note, normal is a synonym to perpendicular. Sometimes we use the word orthogonal as well. So before we show part A, let's do just a little bit of background. Suppose I have the point 1, 1. And then I also have the point, say, 3, 4. And I want to draw the vector from 1, 1 to 3, 4. How could I write this vector? And we'll call it vector v. Well, vector v is really the change in x, comma, the change in y. You've probably seen this before when you studied vectors. So I could say that the vector v is my change in x, x2 minus x1, for example, and then comma, the change in y, which will give us the vector 2, 3. Now, the main point that I want to show in this simple example is the relationship between the vector, between 2 points, and the slope. Because we know that the slope of a line is given by delta y over delta x. So now let's look at part A. And we'll consider the line ax plus by plus c equals 0. And let's do a little bit of a rewrite. We'll say by equals negative ax minus c. And then y equals negative a over bx minus c over b. Now what I really care about here is my slope. Because in my line, ax plus by plus c equals 0. And I'll just draw a random example for that line. Something like that. And if I were to pick 2 points on that line and draw a vector, I could find its slope by doing delta y over delta x. But that would also help me find my vector. So I'll call vector v again from the first point to the second point. So vector v could be written as, for example, change in x, which could be b, right? Because my slope is negative a over b, that can be written as delta y over delta x, any proportion that matches that. So I certainly could say delta x could be b, which would make delta y negative a. And then a vector normal to that, that is perpendicular, which I'll call the vector n. My claim is that a vector normal to v could be a comma b. This is a very simple proof, because if I take the dot product of these two vectors, I'll do n dot v, which is a comma b dot b comma negative a, I get a times b plus b times negative a, which equals 0. Now recall that the cosine of the angle between two vectors is given by one vector, so I'll say n dot v over the magnitude of n times the magnitude of v. So if n dot v is 0 over some number, that means the cosine of theta is 0 which of course means that theta is 90 degrees or pi over 2. So a vector normal to the line ax plus by plus c equals 0 could be given by a comma b. Or really, n in general is any multiple of that vector a comma b. So now let's look at part 2 of this, or I'll call it part B. And we want to show that the distance from some point, and we'll call that point x1, y1, to the line, or to a line, ax plus by plus c equals 0, is given by the following. The distance equals ax1 plus by1 plus c, absolute value, because it's a distance, we'll make sure we have the positive value, all over a squared plus b squared. So how can we show that this is true? Well, let's start by drawing a picture. Just going to draw just a random line. We'll call that the line ax plus by plus c equals 0. And then we're going to have some point off the line. It could be on the line, but we're going to have a point off the line. We'll call it point P, which would be x1 comma y1. And then we're going to draw another point, just a random point somewhere on the line, which we'll call Q. We'll call that x naught comma y naught. Now the distance from a point to the line, or a point to anything, is going to be perpendicular to it, or normal to it. So I'm going to draw another normal line, but I'm going to draw it from point Q. So this would be my normal line. And it could extend out. Let's make my normal line a little bit longer. And then I'm going to draw the vector PQ from Q to P. And one last thing in my picture, I want to draw the projection of PQ onto N. So if you haven't watched the video on projections, I suggest you go back and watch it now. So the length that we want, which I'll call D, is going to be the projection of PQ onto N. Now, a reminder that the projection of a vector onto another one is given by the following. So it's going to be n dot pq over the magnitude of n squared times the vector n. This is what we saw in the video on projections. I'm going to write this one in a slightly different fashion. So the projection of PQ onto my vector n, I can write as n dot PQ, which is a number, it's a scalar, all over the magnitude of n, which is a number. And then I'll take one of those magnitudes of n's and put it off to the right. So we have something like this. And the reason I did this is because the vector n over magnitude of n is a unit vector, which means its magnitude is 1. So if I want to find the magnitude, how big the projection of PQ onto n is, I can simply take the absolute value, because I only have scalars at this point, right? A dot product is a scalar, a magnitude is a scalar. So I can take the absolute value of n dot pq over the magnitude of n, which is already positive. And once again, I only need to find the magnitude of this left part because the magnitude of this right part is 1. So let's do the dot product over here. Actually, let's get a little bit more information. I'll rewrite it so we can see it. PQ is going to be the vector x1 minus x naught, comma, y1 minus y naught. And then as we saw in the first part, a normal vector can be given by a b, where this is the a and this is the b, which are both found in the line. So if we find the magnitude of the projection of PQ onto n, we get n dot PQ, so I would have AB dot x1 minus x naught, comma, y1 minus y naught, all over the magnitude of n, which is the square root of a squared plus b squared. So we already have the denominator matching what we try to make a match. And let's do the dot product of the top part. We get ax1 minus ax naught plus by1 minus by naught, and then all over the magnitude of n, square root of a squared plus b squared. Let's rearrange the top slightly. I can write as ax1 plus by1, and then minus ax naught plus by naught, in parentheses there, over the square root of a squared plus b squared. Now if we look back at our equation, which I'll write one more time for us, ax plus by plus c equals 0, notice that I could write c equals negative ax minus by, which is true for any x and any y pairs on the line, which means that we could write our distance between the point and the line as ax1 plus by1 plus c all over the square root of a squared plus b squared. Let's do one really quick example. Let's find the distance between, let's say, the point 2, 4 and the line 3x minus 2y plus 1 equals 0. Let's set some of these things up. The 3 is going to be our a. The negative 2 is going to be the b. 1, positive 1 is c. And then x1 is 2 and y1 is 4. So all we have to do is plug these things into our formula up top, and we get the distance is a times x1 plus b, negative 2, times y1 plus c all over the square root of a squared, 9, plus b squared, 4. And if we simplify this out, we get 6 minus 8 plus 1 over the square root of 13, which equals negative 1, but absolute value. So 1 over the square root of 13.